Welcome to homework.
In this problem, we want to calculate the values of the change in Gibbs free energy at standard conditions of formation for both Fe2 plus and Fe3 plus aqueous species. We can use the equation that delta G equals negative NFE in order to solve for the overall change in Gibbs free energy of each one of these half reactions. And then we can use the equation to find the overall change in Gibbs free energy based on the overall change in energy for the products minus the reactants. So the equation on the top is the half reaction that involves Fe2 plus ions. And we see that it has a value for the cell potential of negative 0.44 volts. So starting with that, we can find the change in Gibbs free energy for that half reaction to be equal to negative NFE, where N is the number of moles of electrons, which we see we have 2 of those. So that's 2 moles of electrons times F, Faraday's constant, 96,485 coulombs per mole electron times the cell potential, which is negative 0.44 volts or joules per coulomb. And so when we calculate that all out and we divide by 1,000 to get this in units of kilojoules, we see that delta G at standard conditions of this half reaction is about 84.9 kilojoules. And now we know that this is equal to, that delta G of this half reaction of 84.9 kilojoules is equal to the total change in Gibbs free energy of the products minus that of the reactants. On the products, we just have solid iron, and that has a change in Gibbs free energy at standard conditions of formation of 0. So the products is 0 minus the total change in Gibbs free energy at standard conditions for the reactants. We know that the electrons have a change in Gibbs free energy at standard conditions of formation of 0. And so this is the change in Gibbs free energy at standard conditions of formation of Fe2 plus ions. And so when we take over and divide by the negative, we see that the delta G at standard conditions of formation for Fe2 plus ions comes out to negative 84.9 kilojoules. And now we see that we have 2 half reactions involving Fe3 plus ions. So we can go through each one of these and verify that we get the same answer either way. So starting with that middle reaction, the value for the cell potential is 0.77. So we can begin by solving for delta G at standard conditions again, using delta G equals negative NFE. This time N, we have 1 mole of electrons. Faraday's constant is the same, 96,485 coulombs per moles of electrons. And the cell potential this time is 0.77 volts or joules per coulomb. And so for that half reaction, the change in Gibbs free energy comes out to about negative 74.3 kilojoules. And that is equal to the change in Gibbs free energy of the products, which is the 1 mole of Fe2 plus times the change in Gibbs free energy of formation at standard conditions of Fe2 plus, which is what we solved for before, so negative 84.9 kilojoules. Minus the change in Gibbs free energy of formation total of the reactants. So for the electrons, that has a delta G of formation value of 0. And so we are left with the delta G of formation at standard conditions of Fe3+. And when we rearrange, we find that delta G of formation at standard conditions for Fe3+ ions comes out to about negative 10.6 kilojoules. And now we can solve for this using the other half reaction just to verify that we get roughly the same answer. So this time the cell potential is negative 0.036 joules per coulomb. So that means delta G is equal to negative N. This time we have 3 moles of electrons times Faraday's constant times negative 0.036 joules per coulomb. And that comes out to about 10.4 kilojoules. And so delta G, 10.4 kilojoules, is equal to, based on that third half reaction, 0 for the products, because we just have solid iron. Its total change in Gibbs free energy of the products is 0. Minus, for the reactants, we have delta G of formation value for electrons to be 0. So that just leaves us with the delta G of formation at standard conditions for Fe3+ ions. And so we see that that means that delta G of formation for those Fe3+ ions comes out to negative 10.4 kilojoules. When we compare that to what we calculated previously, negative 10.6 kilojoules, we see that those are very close to one another, and error can be attributed to rounding off. And so those are the 3 values for the delta G of formation for those 2 ions, where we calculated for Fe3+ that value twice.